Imagine standing at the edge of space. The Earth sprawls beneath you, a breathtaking tapestry of blue and green. The stars are a dazzling backdrop, cold and distant. You take a deep breath, the thin air a stark reminder of the emptiness that surrounds you. And then, you leap. What would happen next? It's a question that has captivated humanity for centuries. The dream of space travel, of venturing beyond our planet, is intertwined with the fear of falling back to Earth. The vastness of space is both alluring and terrifying. Falling from this height is not just a physical challenge, it's a test of our understanding of the universe and our place within it. Many believe that there's no gravity in space. This is simply not true. Gravity is what holds the moon in orbit around Earth. It's what keeps our planets bound to the sun. Astronauts appear weightless because they're in a constant state of freefall. They're still being pulled towards Earth, but they're also moving horizontally at incredible speeds. This creates the illusion of weightlessness. Gravity is a force that attracts any two objects with mass. The more massive an object, the stronger its gravitational pull. Earth's gravity is what keeps us grounded, and what would make a fall from space so perilous. On October 24, 2014, Alan Eustace, a Google executive, made history. He jumped from a balloon in the stratosphere 25 miles above Earth. This daring feat set a world record for the highest altitude freefall jump. Eustace wore a specially designed suit to protect him from the extreme conditions of the stratosphere. The suit provided pressure, oxygen and insulation against the frigid temperatures. His descent lasted several minutes and included a period of supersonic speed. Eustace's jump demonstrated the human spirit of exploration and the technological advancements that make such feats possible. Falling from space, however, is a far different challenge than jumping from the stratosphere. The primary danger lies in re-entering the Earth's atmosphere. When an object enters the atmosphere at high speed, it encounters friction from the air. This friction generates an intense amount of heat. This is why spacecraft need heat shields to protect them during re-entry. Without a heat shield, an object falling from space would simply burn up in the atmosphere. This intense heat is why we see meteors burning up as shooting stars. They are chunks of space debris that enter Earth's atmosphere and are vaporized by the heat of friction. Section 5. The long fall. While gravity is a powerful force, falling from space wouldn't be an immediate plummet to Earth. Instead, the process is much more gradual and complex. Objects in orbit are essentially in a constant state of freefall. This means they are perpetually falling towards Earth but never actually reaching it. They're constantly being pulled towards Earth, but they're also moving horizontally at such a high speed that they keep missing it. This delicate balance is what keeps them in orbit. This horizontal velocity is what keeps them in orbit. Without it, they would simply fall straight down due to gravity. To fall back to Earth, an object needs to slow down its horizontal speed. This reduction in speed can be achieved through various methods. This can be achieved through atmospheric drag or by firing thrusters in the opposite direction of travel. Atmospheric drag occurs when an object encounters the thin layers of Earth's atmosphere, gradually slowing it down. The International Space Station, for example, orbits Earth at a speed of about 17,500 miles per hour. This incredible speed allows it to circle the planet approximately every 90 minutes. It's constantly losing a tiny amount of speed due to atmospheric drag, but it periodically uses its thrusters to boost itself back up to a higher orbit. This ensures it remains in a stable orbit and doesn't gradually descend towards Earth. The thrusters provide the necessary push to counteract the drag and maintain the station's altitude. Without these adjustments, the station would eventually lose enough speed to re-enter Earth's atmosphere. Re-entry is a carefully controlled process requiring precise calculations to ensure a safe descent. The object must enter the atmosphere at the correct angle and speed to avoid burning up or skipping back into space. Once the object has slowed down sufficiently, parachutes are often deployed to further reduce speed and ensure a gentle landing. This marks the end of the long fall from space. Section 6. The need for speed. The speed at which an object falls from space is determined by several factors, including its initial altitude, its shape, and the density of the atmosphere. When an object begins its descent from the vast expanse of space, it encounters different layers of the atmosphere, each with varying densities. These layers play a crucial role in influencing the speed and behavior of the falling object. The higher the altitude, The longer the fall and the faster the object will be traveling when it reaches the denser layers of the atmosphere. At higher altitudes, the atmosphere is much thinner, offering less resistance to the falling object. This allows the object to gain significant speed before it encounters the thicker layers of the atmosphere closer to Earth. As the object falls, gravity pulls it towards the Earth, causing it to accelerate. This acceleration continues until the object reaches a point where the force of gravity is balanced by the resistance of the atmosphere. The interplay between gravity and atmospheric resistance is a fascinating aspect of physics that governs the behavior of falling objects. However, as the atmosphere gets denser, air resistance increases, acting as a counterforce to gravity. This resistance, also known as drag, works against the acceleration caused by gravity, gradually slowing down the object's descent. The denser the atmosphere, the greater the drag force exerted on the falling object. Eventually, the object reaches its terminal velocity, the point at which the force of gravity is balanced by air resistance. At this stage, the object no longer accelerates and continues to fall at a constant speed. Terminal velocity is a critical concept in understanding the dynamics of objects falling through the atmosphere. For a human skydiving from an airplane, terminal velocity is about 120 miles per hour. This speed is reached after a few seconds of freefall, and the skydiver experiences a sensation of floating as the forces of gravity and air resistance balance out. The experience of reaching terminal velocity is both thrilling and scientifically intriguing. However, an object falling from space would be traveling much faster due to the greater distance and the thinner atmosphere at higher altitudes. As it descends, it encounters increasing atmospheric resistance, which eventually slows it down. The journey of an object from space to Earth is a complex interplay of forces, showcasing the incredible dynamics of our planet's atmosphere. Section 7. Shielding against the Inferno. Surviving a fall from space would require more than just a sturdy spacesuit. The vastness of space and the thin atmosphere of Earth present unique challenges that demand advanced technology and innovative solutions. The primary challenge would be to dissipate the immense heat generated during atmospheric re-entry. As a spacecraft hurtles towards Earth, it encounters air molecules at high speeds, causing friction that generates intense heat. A heat shield, like those used on spacecraft, would be essential. This shield acts as the first line of defense against the searing temperatures that can reach up to 1,650 degrees Celsius or 3,000 degrees Fahrenheit. A heat shield works by absorbing and redirecting the heat away from the object it's protecting. The materials used in these shields are specially designed to withstand and manage extreme thermal loads. The material of the heat shield is designed to ablate, meaning it vaporizes at high temperatures, carrying away the heat energy with it. This process of ablation is crucial for maintaining the integrity of the spacecraft. The shape of the heat shield is also crucial. Engineers have found that a blunt shape is most effective in creating a protective barrier. A blunt shape, like that of a capsule, creates a shock wave in front of it, which helps to dissipate some of the heat. This shock wave acts as a cushion, reducing the thermal load on the heat shield itself. The combination of advanced materials, ablation processes, and strategic design ensures that the spacecraft can survive the fiery descent back to Earth. Without these innovations, re-entry would be an insurmountable challenge. Engineers and scientists continuously work on improving heat shield technology, testing new materials and designs to enhance safety and efficiency. Their relentless efforts push the boundaries of what is possible in space exploration. Ultimately, the success of a mission depends on the reliability of these heat shields. As the spacecraft safely lands back on Earth, it stands as a testament to human ingenuity and the relentless pursuit of knowledge. Section 8. A controlled descent. Even with a heat shield, surviving a fall from space would require a controlled descent. Simply plummeting towards Earth would result in catastrophic forces upon impact. A parachute system, similar to those used by skydivers but capable of withstanding much higher speeds, would be necessary. This parachute system would need to be deployed at a precise altitude and time to ensure a safe landing speed. It would also need to be large enough to create enough drag to slow the descent effectively. Additionally, a backup system, such as smaller drogue parachutes to help stabilize the descent, would be crucial in case of a malfunction with the primary parachute. Section 9. The future of falling. As we venture further into space, the ability to return safely to Earth becomes increasingly important. Understanding the challenges of falling from space is not just an academic exercise, it's crucial for the future of space exploration. New technologies such as inflatable heat shields and advanced parachute systems are being developed to make space travel safer. These innovations could one day enable us to return to Earth from orbit or even from other planets. The human desire to explore is boundless. As we reach for the stars, we must also find ways to return safely to the planet we call home.